Not, I guess we're recording. So let's see here. Let's share the screen. Okay. You guys see that okay?
Yep.
Yeah. Okay, good. So the last class we started in on basically continuous superposition. All right. And so we're continuing that because where we'd left off was just sort of the setup for the thing. It's like I said, okay, we're going to do a continuous superposition that's going to involve basically going from um, essentially phi p to psi x. Sorry, it's bad notation. Phi of p to psi of x in time or at time 0. And we said that this operation would be Fourier transform. And then going in the other direction, psi of x to some function phi of p is an inverse Fourier transform, which throws me off every time because, you know, outside of quantum class, where do I do Fourier transforms? Well, as they were originally used, which is frequency and time. And I always want time to be sort of x and frequency to be p. And this kind of reverses that as far as nomenclature goes. Right. So we'd done this, we'd set up like this is what these transforms look like. And then essentially we said we're out of time for the day. Today we're going to start with what if we give this function some functional form. And so what we do is we're going to give it the simplest functional form for a Fourier transform perspective, which is the Gaussian. Why is that the simplest form for Fourier transform purposes? Because Fourier transform of a Gaussian is a Gaussian. So these two functions will both therefore end up being Gaussians if everything is done right. Now, as a reminder, the Gaussian distribution looks like this for some generic variable. We'll call it squiggle, everybody's favorite. So the Gaussian distribution, maybe I should say the Gaussian distribution really is f of squiggle, is 1 over, oops, left off my thing, 1 over sigma square root 2 pi, where sigma is going to be standard deviation, which is the width in some sense of this, e to the negative of squiggle minus sort of the central peak or the average value of squiggle squared over 2 sigma squared. All right, so this of course is our standard normal distribution. It's symmetric about this axis despite my bad drawing. My bad drawings are even worse on this, by the way, than in class, for the simple reason that the board that I'm drawing on is actually sitting in my lap, but this all shows up on my screen. I don't know if I've ever really explained that. So this right here would be squiggle average. And then your standard deviation for this is going to be out here, such that if this right here has a value of 1 over this right here. And this value right here, you've essentially fallen by a squiggle up here, squared. Okay, so you've got by a standard deviation squared up here, I mean. And so then you're dividing that by 2 sigma squared. Now you may be wondering, why by 2 sigma squared? Why not just by sigma squared? Well, remember that this right here is, in some sense, a probability density distribution that you then have to square it in order to get the actual amplitudes, which you then integrate to find probabilities. By squaring it, you have an exponential. You basically double the power in the exponential, and that means that the sigma is the 1 over e for the amplitude squared, but it's e to the minus half over this same value. That's your y-axis value. For what it's worth, this e to the minus half has a value of about 0.606. This is just kind of the generic, right? So now we say, all right, what does that look like in terms of momentum space? So Gaussian momentum distribution. The function basically looks like this. Phi of p is 1 over 2 pi beta squared all to the half power, all to the 4th power, as it turns out. E negative p minus p naught squared over 4 beta squared. So essentially, we're making beta kind of be like our standard deviation value, but kind of modified a little bit. Like there's an extra factor of 2 here, so that kind of implies an extra factor of √2. And that implies an extra factor of √2 up here, as it turns out. Hence why this works out to the 4th power somehow. This distribution obviously is going to look more or less the same as the other one, but we can now kind of label it in terms of betas and p's and p naughts. So the distribution itself, again, is kind of this nice bell curve, and I've kind of cut it off before the ends. Like these have to be asymptotic at some point in order for the area of this to be 1. This obviously is my phi of p axis. This right here, my p axis. And if I label a few points of interest, this central point in here would be p is p naught. And then what we have is a width at some point of 2 beta. So let's say this right here has a value of phi of p naught. Then we have e to the negative 1/4 phi of p naught. And that ends up being basically somewhere in here. And that has a width, for what it's worth, of 2 beta. Okay. And then our e to the half is right in here, e to the minus 1/2 phi of p naught. And this right here, we drop down onto these axes. This is like your standard deviation. This is plus square root 2 of, whoops, I said b naught, it's just beta. And this is your minus root 2 beta from p naught. Okay, so p naught is where the peaks, distribution peaks value is. The scale factor in front of this right here ensures proper normalization for our system. And then if you wanted to do probability distribution, this is not how we've been doing probability distribution. Probability distribution comes out like this. Too many things are P, projection, probability, probability distribution, lowercase p for momentum. Fun times. Okay, this is momentum probability distribution. All right, and so this right here would be this thing squared. So you end up with your 1 over beta square root 2 pi e to the, and we're squaring this, so that means multiply everything by 2, negative p minus p naught squared over 2 beta squared. And so that's actually a Gaussian distribution. This other thing also is a Gaussian distribution. It's just that stuff doesn't line up quite the way it's supposed to. Things don't line up sort of 1-to-1 with our usual sigma and beta are the same thing, etc. Okay. So now what we do is we say, all right, maybe we want to know what are the expectation value and the uncertainty value. So expectation value, this is the one that's going to have, specifically for momentum, P. And looking at the symmetry of this system, we know that the answer is going to end up being P naught. Okay, and then uncertainty value, or momentum, of course. We did the expectation value of momentum, now we need the uncertainty of momentum. And so that would be delta P. And again, that equals beta. Okay. So now let's go ahead and consider the time evolution for the system. Okay, so time evolution is, we want to figure out what is psi of x comma t. And the answer is we got to do this Fourier transform. We have root 2 pi h bar times 1 over 2 pi beta squared to the quarter e to the negative p minus p naught squared over 4 beta squared. And then the Fourier transform part of it is this guy, and then e to the I times p times x whoops, it's over h bar dx. So this right here is your phi of p. And then this part right here is sort of your Fourier transform portion. Oops, we forgot something though. I said that I wanted to do this in time dependent. So this is like at time 0. If you want to include time dependence, you've got to also have your e to the negative I p squared t over 2 mh bar. I think I wrote dx before. It's supposed to be dp. We're trying to get it into x. So this right here is time dependence. From Schrodinger. And then these two elements are the Fourier transform part. Okay. So what's the answer to this integral? It's a pretty long integral. We could maybe combine some terms. Essentially, the usual way to do it is you either throw it into Mathematica or Maple and see what comes out, and then see if what comes out makes any sense. Or you might try to look it up in a table of integrals. And so like in your textbook, the integral table, you have appendix X. And then of course, if you're in the class, you should have access to that integral table that I posted into Canvas. In Dr. McIntyre's integrals table, I believe it is essentially equation f dot 23. So appendix X, this equation. And essentially what the result ends up being for this thing is psi of x comma t is square root of 2 beta divided by h bar gamma. That's a square root. And then essentially the fourth root of 2 pi. I'll define gamma in a moment. E to the I times P0 x minus P0 t over 2m all over h bar. And then e to the minus x minus p naught t over m to the 1 power, over 1m squared, beta squared over h bar squared gamma. Okay. And our new parameter gamma is defined as 1 plus I t over tau, for tau defined as m h bar over 2 beta squared. Okay, so some comments about this thing. Let's select this guy. No, it's not the selection I wanted. It's not the selection I wanted either. That's not going to have the selection I wanted. I really, really hate the lasso tool, and I hate the fact that it defaults to that when I want to select stuff instead of defaulting to the box tool. But I guess that's life. So some comments about this thing now that we're here. Well, for starters, this is a Gaussian. So you have a bunch of stuff here. And then this part right here has the correct form for a Gaussian. Except for that, this is now like X, and this is like your X bar, which is V P naught over M times T. So this portion right here is the Gaussian part of our Fourier transform. This right here is basically giving us phase. Okay, comment number 2. Notice that this right here suggests, once again, V phase is P naught over 2M. And this right here suggests that V group is P naught over M. And, you know, if we're really honest about this, we might call it like the average of each of these. But the reason why we don't put an average on it is because, again, this right here implies carrier. So this whole term right here is the carrier term. And so this right here, this sort of like average value is also the carrier value for this. And this right here is the group value for all of this. The whole group moves, you know, if this was a motion, the whole group would be moving like so. But again, this isn't really a motion. This is more like in space. Let me think for a minute here. Let's give ourselves another new term. So let alpha be defined as h bar over 2 beta. No, sorry, I'm getting ahead of myself. We have a beta down here. Fine. The beta over here is now apparently a numerator term within this exponential. Remember that was how wide the distribution was in momentum space. So this would be inverse. How wide is it in, well, space representation. So the wider in momentum, the narrower in space, and vice versa. Okay, so that goes with our uncertainty principle for starters. And it goes with our observations about bandwidth versus pulse duration when we're talking about times. Okay, so with that little thing aside, now let's let alpha be defined in this way. If that's the case, then our wave function psi of x comma t can be redefined as 1 over 2 pi alpha squared to the 4th power times 1 over root gamma, or in other words, you could maybe put a gamma squared in here if you wanted, e to the I p naught times x minus p naught t over 2m all over h bar, e to the negative x minus p naught, left off a squared here, sorry. Did I leave off a squared here? I don't think I did. I'm sorry, this term is not squared. sometimes these notes. P naught over m times t. This term does have to be squared, though, for it to be Gaussian. Divided by 4 alpha squared gamma. This just kind of simplifies our equation slightly. So we've got our carrier wave or our carrier term. We've got our Gaussian. The Gaussian, for what it's worth, is the envelope. Which you've seen before. And then I think, by the way, your book may have a typo at this explanation. I think he maybe has a typo, unless they fixed it in the Cambridge edition, with where they characterize phase velocity versus group velocity. But these are correct. These are the correct values. Now, if we isolate the envelope itself, we can basically calculate spatial probability densities. And, how do we do that? Well, remember that, oops, let's go here. Remember that our probability densities, let's say of x comma t, are going to be this thing squared. All right, so this will isolate this component, because when you square this thing, you're multiplying by complex conjugate, which makes the thing real, or in other words, makes this part go to 1. And so what's left over is essentially 1 over alpha. I'm going to use a capital gamma here, root 2 pi, e to the negative x minus p naught over m t quantity squared, divided by, rather than 4, we now have 2 alpha squared gamma squared. And so in looking at this, you can see that gamma must be defined as essentially the root of little gamma. And so that is the root of 1 plus t over tau squared. Okay, so again, this is a Gaussian in which these terms right here, this alpha squared gamma squared term, is sort of like the sigma squared term in our generic Gaussian. Okay. And furthermore, if you look at where everything is down here, this guy right here would therefore be akin to a sigma term, just like in our original, whoops, gotta go up one more, our original Gaussian. So this matches the Gaussian sort of beat for beat, if you will. So what does it look like? Now comes my bad drawings again. But if you want to open up the McIntyre text, you know what? I may actually have this on my computer. So this is figure 6.8. Let me see if I've got it on my machine, rather than having to try to hand draw it. Gonna throw this out of the way. And yes, here we go. So looking for figure 6.8. So here it is. There we go. So you're looking at the real part of psi of x. The dashed line is your envelope. The squiggly line is sort of your carrier. And so the squiggly line actually is what the function itself looks like. So this right here really is, now somebody's knocking on my door. This right here really is the real part, psi of x. Spacing is carrier frequency. We'll call it carrier spacing. This dashed line is the envelope, which is a Gaussian. And then when you go to do your probability, this right here is what that's going to look like.
Dr. Sanders.
Okay, and this is Gaussian, yes.
Does every wave packet have a Gaussian distribution?
No.
Okay.
No, it doesn't. Not everyone does. We started with the assumption that what we're going to work, it's not even an assumption. We just started with the explicit statement that we are doing a Gaussian.
Okay. Okay.
But no, you don't have to have a Gaussian. Case in point, like let's say that we decided we were going to play different sound waves, right? So this is always dangerous. Let's open up a thing here. Frequency tone generator. Let me turn on my computer sound so that you can hear this. And I hope that it's not too loud when I first do it. Let me see if I can find. You hear that?
Yep.
Okay. So, here's a pure wave. Just a single sine wave, kind of equivalent to a single frequency mode, and therefore a single momentum mode. But I can change it like that, or this, or that, by essentially changing what the relative values of these different frequencies are. Okay, and so I can do something similar with my momenta distribution. Let's share again, but now share this screen. And therefore shape what my sort of superposition looks like. Okay. But this is actually a fairly standard type of distribution. And it's also very much the easiest to work with in terms of doing Fourier transforms. So there is that. This is kind of a logical stopping place, even though we're a little early today. it's kind of a logical stopping place for the notes. The next thing that we would do is basically discuss expectation values and then uncertainty principles and so on. But I don't think that I can get anywhere meaningful in 3 minutes, 2 minutes. And I'm not sure that I want to stop in the middle of that.
Okay.
So we'll call it a day here. We'll stop it here. Yes,
So-
he.
Just a quick question. Can you give us a sense of what to expect from the exams? I didn't get your Quantum 1 class, so what yes to do.
Gosh, it's, I haven't taught this class even in great value version in it's been 3 years since I last taught this.
Okay.
I had to think about it. It's been long enough. It was the spring after COVID. So it's like we were back on campus again for the first time, but still in pods. But for this class, we were like actually present. And my exam questions tended to be straightforward. Maybe I pulled one out of the book and then I'd make one up, and then I have like a whole set of multiple choice style questions that I sometimes trot out for the first page.
Okay. Is it
Conceptual questions is what I'm trying to say.
Sure. Are we allowed notes, or is it open book, or what's the format there?
So what I did in Quantum 1 was I let everybody have 1 page of notes.
Okay.
And so we will continue with that and the integral tables, because for this one, if you're having to do integrals and these integrals are not like, yeah, if you happen to work in this field daily, and so you're doing this function quite a bit and this integral quite a bit, maybe you can write out this solution from, yeah, I know it. Certainly, like I would hope if you saw this function in the integral, you'd mentally rearrange stuff, recognize that it's a Fourier transform of B, a Gaussian, and that therefore C, the result, will also be Gaussian. But you may get some of these details wrong otherwise. Like, that it's going to have to be an X minus X naught squared, essentially.
Yeah.
Over some delta X, essentially, or some sigma.
Okay.
But I wouldn't necessarily expect, especially for like you guys who at least in principle, based on where you are in your careers, aren't just doing Fourier transforms on a regular basis by hand to therefore recognize the exact result of this.
Yeah.
It's like, yes, I expect that that this is a Gaussian and that a Fourier transform has happened. And I expect for you to know that means that you're going to have a Gaussian on the other end, and that it should be some function of X rather than of P. But beyond that, just look it up in the table.
Okay. And what I guess my last question is, what sort of timeline are we looking at for this first exam?
Fair. So I have a meeting on February the 12th.
Okay.
And I think that we're not going to have class that day as a result of that meeting. Now, what that looks like, I haven't quite decided.
Okay.
I think that the best way for us to do exams is for you guys to show up and do the exam.
Sure.
Not, like I have done it before where I've tried to proctor it virtually, but it's just better for you to show up and take the exam.
Yeah.
Now, one possibility is that all three of you show up Monday at 11, and I just give Miss Hazel 3 copies of the exam and say, watch them for an hour to take this exam
Okay.
while I'm in this meeting. And the
Yeah.
meeting probably actually will end right around the time the class ends, maybe slightly earlier. But usually by the time that meeting's over, I'm done and I just need to go get lunch. So I don't think that I am planning to necessarily be back here to proctor it, but we will have something set up for you to do that.
Okay.
And if, especially in your case, if you're not able to be here on Monday for whatever reason, then we schedule a makeup day and time.
Okay.
That's
Sounds
how
great.
I've usually done it. Oh, did I stop recording? No. Okay.